Okay, we're going to be talking about factors that affect solubility today. So here's a couple things that we have going on. One is the common ion effect and how the common ion effect can affect solubility. So we're given the example here of calcium fluoride being placed in water. So first thing we're going to do is we're going to write a dissociation equation for calcium fluoride in water. Here's our calcium fluoride solid. We're placing it in water. And we have some calcium ion, well, plus we have some fluoride ion and coefficient of 2 there. These are going to be our aqueous solutions. Now, if we look to the KSP value, the KSP value is actually quite low. It's 3.9 times 10 to the negative 11th. So as it is, calcium fluoride, we would say that this equilibrium lies very much to the left. So very little calcium ion and fluoride ion are being given off into solution, and we have mostly a solid calcium fluoride at the bottom of a beaker. If we put it in a beaker, undissolved, even though a small amount will dissolve, very, very small amount. Now, just a quick review on Lachat-Liaised principle. We've talked about Lachat-Liaised principle before, is if I could change the equilibrium, the shift in the equilibrium by doing a couple things. One of the things that I could do is I could cause the equilibrium to shift left. Now I could do that by adding more calcium or adding more fluoride. Now, if we shifted left, we would say that we reduce solubility because reduction in solubility would be more solid on our left-hand side or our reactant side and less of the fluoride product and the calcium product, whatever we did to shift this to the left. And if we said we shifted to the right, whatever we did to shift to the right, and we could do a few different things we know as remembering our Lachat-Liaised principle, this would increase solubility. So we'll just say a shift to the left is going to reduce and a shift to the right is going to increase. Now let's take this example and talk about, let's say we had some calcium fluoride placed into solution, we had an equilibrium established, and then what we did is we added some sodium fluoride to the solution. Now, what would happen is obviously the sodium fluoride is going to ionize. Sodium is because sodium is an alkali metal, it's very soluble. So we're going to have the sodium ion plus we're going to have the fluoride ion. Now, what this is going to do is we are increasing the concentration of our fluoride ion. And we know if we increase the concentration of our fluoride ion, we're going to shift this entire equilibrium to the left. And what that's going to do is going to reduce the solubility of the calcium fluoride. So by adding a common ion, and that's really what's going on here, the fluoride is the common ion. By adding a common ion, we can reduce solubility within this equilibrium. Now, there is one other thing that I want to mention with respect to this equilibrium mixture, and that's this. We've talked about how we can shift this to the left, and one of the things that often students make a mistake about is they say, well, what if I was to add more calcium fluoride? That would cause the equilibrium to shift to the right. And the answer is no, that will not cause a right shift. And the reason is once we get to an equilibrium, and we could draw a little model of what this equilibrium would look like. Let's say once we get to an equilibrium where we have some calcium fluoride solid at the bottom of our beaker, and we have some calcium ions up in our beaker, lots of fluoride ions, well, maybe not a lot, but a bit. We know we're at equilibrium when no more calcium fluoride will dissolve in a given amount of solution. And we have equal rates of ions being dissolved and equal rates of ions being crystallized. That is now an equilibrium. By adding more calcium fluoride, all we're going to do is make the pile of calcium fluoride at the bottom of our beaker larger. So just by adding more of a solid to an equilibrium that's already at equilibrium, we just get a bigger pile at the bottom because we are at solubility. We can't, or we are at our solubility for the substance, we cannot add more and just suddenly magically have it dissolve more. The next thing we're going to talk about is solubility and how pH is going to affect solubility. And so let's give us a reaction here. We're taking some solid magnesium hydroxide and adding it to water, and we'll get some magnesium ions in aqueous solution, and we'll also get some hydroxide ions in a solution. Now, this is going to be very similar to our common ion, but we're going to affect it by affecting the pH, which really is a common ion. KSP of this, by the way, is equal to 1.8 times 10 to the negative 11th, which is, again, very small. And so we know that this equilibrium mixture is going to lie very much to the left. We're going to have just a little bit of magnesium and a little bit of hydroxide. And the reasoning behind it is this: why magnesium hydroxide, we would consider it a weak base, not a strong base, because we have less than 100% ionization occurring. So let's add some acid to it. Now, when we add an acid, what that's doing is adding a hydrogen ion, whether it be HCl, HBr, HI, HNO3, whatever. It's all going to be adding a hydrogen ion, and that's really what's going to be affecting things here. And so what this hydrogen ion is going to do is this hydrogen ion is going to react with the hydroxide ion. And we know if we react hydrogen ion with the hydroxide ion, we're going to produce water. Now, what that effectively does is it effectively removes our hydroxide. Now, if we remove a hydroxide or remove something from an equilibrium mixture, that means that equilibrium will now shift towards what is being reduced. So if the equilibrium is going to shift right, what will happen is more magnesium hydroxide is going to decompose, we could say, or dissolve would probably be a better word. We would say more of this will dissolve to form more of the magnesium ion, and it's going to form more of the hydroxide as well. So we're shifting this guy to the right. So by having a right shift, as we mentioned earlier, that would increase the solubility of magnesium hydroxide by adding an acid. Now, before we dive into our examples, let's review something here real quick. We know that we have 7 strong acidic solutions, 7 strong acids that dissociate 100% of the way, and we know what those are. Let's just pick one of them. Let's say we'll pick HBr. Now, HBr is a strong acid. We react it with water. It's going to ionize 100% of the way to the hydrogen ion plus the bromine ion. We would say that the hydrogen ion is our acid, and the bromine ion would be the conjugate base. Now, the important thing to remember is, and this is a review, this is the conjugate base of a strong acid. We talked about this before. We said that if, let's say you have a salt, let's say sodium bromide, and we put some sodium bromide in water, and it broke up into the sodium ion plus the bromide ion. And the question was, does sodium bromide affect the pH of a solution? And the answer was, it does not affect the pH of the solution, because bromide is the conjugate base of a strong acid, HBr, hydrobromic acid. So that idea is going to carry forward here as well. When we have an acid being added to a solution that is at equilibrium, it will affect only weak conjugate bases, or the conjugate base of a weak acid. Now, that's everybody who's not one of the 7 strong acids. So let's look at some of these examples, and we'll see if we can get to an idea of what this is all about. So it says, how will the addition of a hydrogen ion or an acid affect the solubility of each of the following? And we've got zinc carbonate. So we'll just real quickly write zinc carbonate being placed in water. Okay, and so we're going to take a look at this conjugate base right here. Now, this conjugate base is the conjugate base of a weak acid, and that weak acid would be H2CO3, carbonic acid, or we could even say HCO3 1 minus, with the addition of just one hydrogen. So this is a weak acid. So what's going to happen if we do add hydrogen ions, the hydrogen ions are going to react with this to produce HCO3 1 minus. That's going to effectively reduce the concentration of the carbonate ion. Reducing the concentration of the carbonate ion is going to shift our equilibrium according to Lachat Liaised principle. It's going to shift it to the right, and so we would say that this is going to increase solubility. Okay? You can try the next two by yourself if you'd like to pause the video now, and then I'll come back and walk you through them. Okay, hopefully you pause the video and you're not just staring at the screen waiting for me to do it. AgI, we're going to break this up into the silver ion plus the iodide ion. Now we're going to take a look at adding hydrogen, and will it affect pH with the iodide ion. And because the iodide ion is the conjugate base of the strong acid, HI, we would say that this will not affect the pH. And it looks like this last example I gave as bismuth iodide, which is the same exact example as the previous example. I should have chose something else. Again, VII3 is going to break up like this. And again, iodine is the conjugate base, or the iodide, of a strong acid. So we would say that adding acid will not affect the pH, or no. Okay? I want to give you a real life example now of this. This is chemistry. This is a sinkhole, and these occur sometimes. I think the last one I heard about was in Fresno, actually, but this happens all over the world. You'll get something like this where the ground just kind of drops away, and so this is a real life example of chemistry in action. Here's how this happens. Draw a little picture of it first. Let's say we have the surface of the ground here. Maybe somebody standing up here on the surface. That's a surface, person there. And then right below, and we're here in Outwater, and so below us we have a lot of sand, which I can't spell right now. Let's try it again. We have some sand, okay? And then maybe as we dig down further, we might have a layer of clay. And then if we dig down even further, we might have a layer of limestone. Now, what happens is when it rains, which it doesn't seem to be happening very often here in the Central Valley these days, but hopefully it will soon. When it rains, that water will actually start traveling down through the sand. Now, rainwater typically has a pH of not neutral. It's usually about anywhere between 5 and 6. So it's slightly acidic, not very acidic, but slightly. So there is a presence of some hydrogen ions, definitely. Okay. Oftentimes that water then will be slowed down as it goes through the clay. The clay doesn't allow water to transport down as fast as the just sand. But then we get down into the limestone. Now, if we have, let's say, a pocket of limestone down here, if the water has some hydrogen ions in it, which typically rainwater does, those hydrogen ions can react with the limestone. And so let's talk about what happens here. So what will happen then is it actually will eat away at this limestone, leaving kind of a cavern underneath the water, or underneath the ground. Now, once the cavern gets large enough, this could all collapse, and that's what's happening here. Is you get a collapse due to some water seeping down under there and just kind of collapsing the limestone cavern below it that's been eaten away. Now, here's the chemistry behind this whole idea. Okay, so the chemistry behind this is we can take our hydrogen ion and we can react it with the carbonate ion. Now, where does this carbonate ion come from? Well, it comes from calcium carbonate, which is our limestone. Which has very limited solubility. but it, still we can form a KSP value equal to 4.5 times 10 to the negative ninth. And so there's our equilibrium going on. So really, limestone's not going to dissolve readily in just plain water, although a little tiny bit will dissolve, but we get this equilibrium established. Now, what happens is the hydrogen ions come along through the rainwater, which is pH 5 or 6, and they can then react. They can react with the carbonate ion to form this ion, which essentially is going to remove the carbonate ion from our original equation, which is this equation here. And when we remove that carbonate ion, we're then effectively shifting our equilibrium, our original equilibrium of the limestone, this guy right here, we're shifting it to the right, which is going to cause an increase in solubility of the limestone. So once that limestone starts dissolving away, we then get those sinkholes that occur, those huge holes in the ground. Take a look at another thing that comes up, and this is acid rain. And acid rain basically comes from sulfur compounds, usually sulfur and oxygen. We get SO2 gas being given off by the burning of coal and some natural gases and stuff like that, depending on the type of coal. Different types of coal have different sulfur content. And what happens is the SO2 is easily converted into SO3 gas in the atmosphere. SO2 is also a component of smog that you might see sometimes if you drive over to Los Angeles. You see this kind of hazy, sort of gross-looking layer up in the air. That's smog, sulfur dioxide. Now, when you have this SO3 gas up in the atmosphere, and it can react with water, or the SO3 gas, to form H2SO4, which is a nice source of hydrogen ions, right? So normal, like we said before, normal rainwater has a pH of about 5 to 6. Well, when we have this H2SO4 being formed, we can have what we call acid rain with a pH that can drop down to about 4. And that can have some pretty damaging effects on a whole lot of things, including statues, as we see here. And the chemistry behind it is we have this hydrogen ion reacting with calcium carbonate, which is marble. And what's going to happen here is we're going to get, it's just a double replacement reaction. We're going to get the calcium ions in an aqueous solution. We're also going to get carbon dioxide, and we're going to get water. And so if we looked at it as a true double replacement reaction, we really would be forming carbonic H2CO3, but we remember that H2CO3 immediately decomposes into carbon dioxide and water, just like if you took some baking soda and you dumped some vinegar on it, which would be giving it some hydrogen ions, and that would immediately just bubble all over the place where we're producing carbon dioxide and we're producing water. So this is what happens with statues. As you can see, there's a before on the statue. Looks like a little bit of an after there. You can see kind of the statue here sort of being eaten away. So that happens, and there's lots of other examples out there if you want to take a look at those. Okay, that's it for our talk on solubility, and so there will be problems that go along with this.